Hello everyone. uh, in the previous lectures, we have been discussing, in I think the previous two lectures or in one lecture, we have been discussing this important result about groups. This is called the first isomorphism theorem, and we have been applying we have been applying or using the first isomorphism theorem in order to sometime prove something that you already knew or to uh, obtain something that we did not know before. Today we'll try to continue with this first isomorphism theorem. Okay, we'll continue with this first isomorphism theorem. We will apply this first isomorphism theorem to certain specific contexts in order to improve our understanding of first isomorphism theorem, and also to indicate that it can be this is applicable to a very broad context. Undoubtedly, this is a statement regarding group homomorphisms, and there are plenty of group homomorphisms available. So this is certainly applicable to lots of contexts, and we'll discuss some of the interesting instances. Oh, I mean, rather, we will discuss only very few interesting instances, very few interesting applications of the first isomorphism theorem. And this gets used over and over again, and uh, it's difficult to list all the instances where one practically applies the first isomorphism theorem. Certainly, this is applicable to any group homomorphism from G1 to G2. Anyway, so let's have a look at the very first exercise. It says that C cross modulo S1 is isomorphic to the group of the group of positive real numbers. This is a group with respect to multiplication. This is a group of positive real numbers. Okay, yeah, so we are going to establish this using the first isomorphism theorem. And again, the proof is completely straightforward as long as one can come up with a group homomorphism from C cross to R cross, C cross to maybe R cross or R positive, having S1 as the kernel. One of the important maps that you know that is defined on C cross, and that takes values inside R, is the absolute value map, which sends a non-zero complex numbers to its absolute value. And so this is a straightforward to check that this is a group homomorphism that we know, because absolute value of z1 z2 is absolute value of z1 times absolute value of z2, and that for any two complex numbers z1 z2, in particular for any two complex numbers z1 z2 inside C cross. Okay, then one can check that this group homomorphism has exactly S1 as its kernel, and its image consists of all the positive real numbers. So its image is equal to R positive, and its the image of this group homomorphism is equal to R positive, and the kernel of this group homomorphism is equal to S1. Okay, so it follows by the first isomorphism theorem that the domain of this homomorphism, which is C cross modulo the kernel, which is S1, this quotient is isomorphic to the image of this group homomorphism, which is R positive. Okay, yeah, and then we try to see something that you already knew. We'll do so by applying the first isomorphism theorem. Okay, so it says that any finite cyclic group is isomorphic to Z mod n Z for some I think I no, this is fine. Yeah, for some positive integer n. Yeah, of course. This is isomorphic to Z mod n Z for some positive integer Z. Okay, so now we start with a cyclic group, and suppose the element little g is a generator of this cyclic group G. Okay, and we know that there is a unique group homomorphism psi from Z to G. This is straightforward to see. I mean, as long as we impose the condition that psi of 1 is one of the specific elements of G. Okay, and here we specify psi of 1 to be the element G that you have started with, which is one of the generators of the group G. Okay, so since the group G, capital G, is generated by the element little g, it follows that this homomorphism psi is surjective. Okay, and now if you look at the kernel of this group homomorphism psi, that happens to be a subgroup, that happens to be a normal subgroup of Z. In particular, this is a subgroup of Z. Okay, and earlier you have already classified all the subgroups of this group Z. Okay, and since kernel of psi is a subgroup of Z, we know that kernel of psi has to be equal to nz for some integer n greater or equal to 0. Okay, and now again by applying the first isomorphism theorem, we see that z mod nz is isomorphic to g. Okay, for some positive integer n. Once again, since you know that kernel of psi is equal to nz for some integer n greater or equal to 0, we obtained by by applying the first isomorphism theorem that z mod nz is isomorphic to g, and here we see that n is greater or equal to 0. Note that n equal to 0, that we cannot have n equal to 0, because when n equal to 0, this is no different from z, or if you want, this is isomorphic to z. Then since these two groups are isomorphic, it will follow that G is infinite. But you started with a finite group. Okay, so if G is finite, then this n has to be a positive integer. It cannot be 0, and that proves that any finite cyclic group is isomorphic to Z mod nz for some positive integer n. This is something that you already knew, and now you are establishing this using the first isomorphism theorem combined with earlier result where you established or where you classified all the subgroups of the group Z. Okay. Okay, anyway, so what you see is that if G is a finite cyclic group, then it is isomorphic to Z mod nz, and we know that Z mod nz has got exactly n elements. Okay, so the G has to have n elements, or in other words, n has to be equal to the order of G. Okay, so what you have established is that if G is a finite cyclic group, then it is isomorphic to Z mod nz with n equal to the order of G. Okay. Yeah. Okay, so here is an interesting thing to observe. So for example, we know that 2z is a subgroup of 2z is a subgroup of z, and for example 6z is a subgroup of z. So what we have is 2z. So one can consider this quotient 2z modulo 6z, and as used to happen in our school days, that we had the liberty to cancel 2 and 6, in the sense that in the sense that we remove 2 and replace 6 by 3. In that way you will obtain z mod 3z by dividing. So this is something that you used to do in our school days. Whenever you get to see 2 over 6, you could very well replace it by 1 over 3. Okay, so here it comes in the context of groups, so as I was saying that if you just follow high school or maybe elementary school math, or maybe just 5th standard mathematics, then sometime our knowledge of 5th standard mathematics may motivate us to replace 2 and 6 by just 1 and 3, and this exercise says that, well, that can be done, and of course such a statement does require a justification, and here you have the justification, or here you have one such justification. So it says that if we look at mz over nz, okay, so of course one can look at this kind of quotient when nz is contained inside mz. Okay, in other words, one can do so when m divides n. So start with two positive integers m and n such that m divides n, and then you look at the quotient mz over nz. And this exercise says that this quotient is isomorphic to z mod rz, where r is just the ratio n over m. Okay, so this is of course, this isomorphism is not obtained by this high school method of cancelling, certainly not, but one can justify that these two groups are indeed isomorphic. Okay, one can show that these two groups are indeed isomorphic. So let's try to see how to proceed. Again, we will apply the first isomorphism theorem to prove this result. Okay. So start with the homomorphism. This is something actually quite interesting. So you start with this homomorphism psi1 from mz to z. Okay, and then we will consider a group homomorphism from z to z mod rz. That will give us we have a map from mz to z, and then we will define a map from z to z mod rz, and then we will combine these two. In other words, we will compose psi1 and psi2 to obtain a map from to obtain a map from mz to z mod rz. So you'll obtain a map from mz to z mod rz, and then if we have if these maps are suitable, then it will follow that the composition of these two has exactly z mod rz as its image, and its kernel is exactly equal to nz. Okay, so let's see. So you start with this map psi1 from mz to z, where we send any integer k lying inside mz, to the integer m over k. Okay, so note that things are fine in the sense that if you start with an element k of mz, then it is a multiple of m by definition of mz, and if you look at k over m, so it has to be an integer. So psi 1 of k, wherever you are sending it, it does lie inside z. So this map is well defined. Okay, there is no trouble with this. And now of course there is a unique group homomorphism from z to z mod rz, which sends 1 to 1 bar. Okay, by 1 bar I mean the equivalence or the congruence class of 1 modulo the integer r. Okay, so 1 bar is by definition 1 plus rz. Okay, and here this one denotes the integer 1 inside this group of integers. So here we have two group homomorphisms, psi 1 and psi 2, and now if you look at their composition, psi 2 composites psi 1, we end up getting a when you look at this composition, let me write it here, psi 2 circle psi 1, this gives us a map from, or rather a group homomorphism from mz to z mod rz. Okay, and now so now we note that these two maps psi 1 and psi 2, they are surjective. Okay, psi 1 is surjective. I mean, this is quite easy to see. Okay, just from the definition. And again, psi 2, I mean, the fact that psi 2 is surjective follows from the fact that this is cyclic. In fact, follows from the fact that this is generated by 1 bar, and the fact that psi 2 of 1 is equal to 1 bar. Okay, so these two maps, psi 1 and psi 2, they are surjective. So it follows that their composition also has to be surjective. So psi 2 composite psi 1 is also a surjective map. Great. So we have come up with a group homomorphism psi 2 composite psi 1 from mz to z mod rz, and we have observed that this composed group homomorphism is a surjective map. Okay. So now we will try to understand the kernel of this group homomorphism. Okay. So now we pick an element from mz, so which is of this form mk. Suppose this lies inside kernel of psi 2 composite psi 1. Okay, and that will happen if and only if, I mean, the same as saying that psi 2 composite psi 1 sends mk to the identity element of this group, which is 0 bar. Okay. And what is psi 2 composite psi 1 applied to mk? So we first apply psi 1 to mk, and then we apply psi 2. So we apply psi 2 to psi 1 of mk, and psi 1 of mk is by definition equal to k. Okay, and so this statement that mk lies inside the kernel of psi 2 composite psi 1 is equivalent to saying that psi 2 of k is 0, and that is equivalent to saying that k bar is 0. Okay, and that is again equivalent to saying that k is a multiple, saying that k bar is 0 inside z mod rz, that is same as saying that k is a multiple of this integer r. Okay, in other words, k is a multiple of this integer n over m. The same as saying mk is a multiple of n. Okay, so an element of the kernel of this, I mean, if we start with an element of kernel of this, then this has to be of the form this has to be a multiple of n. Okay, so mk has to lie inside nz. Okay, so by this argument we have established that the kernel of psi 2 composite psi 1 is equal to the subgroup nz of the group mz. Okay, the subgroup nz of the group mz. And now applying the first isomorphism theorem, to this group homomorphism. Okay, so you know that the domain of this group homomorphism, okay, modulo the kernel, which is nz. So you get mz modulo nz, that is isomorphic by the first isomorphism theorem to the image of this group homomorphism. And since this is a surjective map, the image has to be z mod rz. So by the first isomorphism theorem, we obtain that mz modulo nz is isomorphic to z mod rz. Okay, so again let's continue all this. So we'll try to apply first isomorphism theorem to some other group homomorphisms also. Okay, so we haven't dealt with matrices for a while. So although I think in the second last problem of the previous lecture we did deal with matrices. Okay, we were studying GLNR, SLNR and so on, but it was essentially it was a straightforward application of this identity. Okay, anyway, okay, great. So we have this exercise. This says that this starts with this group G. Okay, this consists of the 2 by 2 upper triangular matrices of this shape. Okay, it's 2 by 2 upper triangular matrices with non-zero determinants. So such a matrix has to be of this shape: A, B, C, D, with C part equal to 0, and the remaining elements has to be real. And we impose the condition that this is non-zero determinant. In other words, AD has to be non-zero. Okay. And now we look at two subgroups H1, H2 of the group G. Okay, and that this H1 consists of 1 as its first diagonal entry, and the H2 is a subgroup of G consisting of those elements having 1 at the second diagonal entry. Okay, so this exercise says us to show that H1, H2 are normal subgroups of G, and then we need to describe the quotients G mod H1 and G mod H2. Okay, yeah, and as you know that we have been discussing false isomorphism theorem, so let's try to come up with certain maps. Okay, and if you from this group G to somewhere, okay, and if you could show that H1 is a kernel, then it will of some group homomorphism defined on G, then it will immediately follow that H1 is a normal subgroup of G, right? So let's try to do it. Okay, so maybe maybe after going through all these examples, you might be wondering how to come up with all these group homomorphism, how to guess them, how to guess the appropriate group homomorphism that will help us to come up with such an isomorphism. Yeah, if you're wondering about this question, then that's a very nice thing. So this example could somehow motivate you. Okay. See, we are trying to come up with a group homomorphism with H1 as its kernel. So then it makes sense to, send this element to 1. By that I mean, if you send this element to 1, or if you just send, see, H1 is obtained from G, right? I mean, very roughly speaking, H1 can be obtained from G by setting this element equal to 1. Okay, so now if you send this matrix to the element A, to this first diagonal entry, then if you want to understand its kernel, then of course you want A to be, you want this little A to be equal to 1. Okay, provided you are sending this map to a multiplicative group. Okay, then 1 will be the identity element of that multiplicative group. Okay, and then if you set A to be equal to 1, you'll end up obtaining H1. Okay, anyway, this was a nice discussion. We have to make things precise. So here is what we could do. We can define a map psi1 from G to R cross, which sends the matrix AB0D to the real number A. Okay, to the real number A, and then the question is, then of course, as I was saying, we could look at its kernel. But wait, before taking a look at the kernel of this map psi1, we need to make sure that psi1 is a group homomorphism. Okay, so this is something that one can show. So I leave it to you to show that these are group homomorphisms. So we have already defined this map psi1, which sends AB0D to A, and then this map psi2 sends AB0D to D. Okay, yeah, great. And then it is really straightforward to see that psi1 and psi2 are group homomorphisms. Okay, and note that both the maps are surjective, because psi1 sends this matrix to A and psi2 sends this matrix to A. Okay, this holds for any element A inside R cross. Okay, for any element A inside R cross. So psi1 and psi2, they are both surjective group homomorphisms. And if you look at the kernel of psi1 and psi2, you will observe that kernel of psi1 is exactly equal to H1 and kernel of psi2 is equal to H2. Okay, and we know that kernel of a group homomorphism is a normal subgroup, so it follows automatically that H1 and H2 are normal subgroups of G. Okay, and now if you apply the first isomorphism theorem, you will have that the domain of this group homomorphism psi1 G quotiented by the kernel of this group homomorphism psi1, which is H1, is isomorphic to the image of this group homomorphism. Okay, and we have just seen that that this is surjective. Okay, so the image of this group homomorphism is exactly equal to R cross. So what you see is that G mod H1 is isomorphic to R cross, and similarly G mod H2 is also isomorphic to R cross, because psi2 has H2 as its kernel and this map psi2 is surjective too. So it follows that G mod H2 is isomorphic to R cross. And so this is a remainder of this previous proof, where I just stated that one can observe that psi1 and psi2 are group homomorphisms. So I have just stated is I have put it as an exercise here. So please work on it. This is straightforward, but it's good to work on this kind of apparently elementary exercises. Okay, great. Here is another exercise where again one can apply the first isomorphism theorem, or anyway one can also have other approaches, but I cannot imagine any which will not factor through some such thing. Yeah, so this asks to describe the group R cross modulo the subgroup of all positive real numbers, certainly under multiplication of real numbers. So here we define this map from this comes as a hint, so this is not a complete proof for sure. So you can consider the map from R cross to this group plus consisting of plus minus 1, and certainly this is a group under multiplication. Okay, you consider this map, you send x to its sign. Okay, this is a sign map, so you divide x by its absolute value. Okay, then you try to think about it. Okay, and try to see whether you can describe this group R cross modulo the subgroup of positive real numbers. Okay, great. Now you are going to see something interesting. Okay, and again this is something that we have already seen before when we started our we started our lectures on this course MTH 203. I told you I tried to motivate this notion of symmetry a bit. There I mentioned that if you consider all the bijective maps, or maybe if you consider all the bijective maps f from x to x, then the set of all of such bijective maps forms a group, okay, under the composition of functions. Okay, and we for next few lectures we will focus only on such maps. Okay, we'll start with the set x, and we'll focus on the bijections from f. We will focus on the bijections f from x to x. Okay, and we'll do so when the set x is finite. Okay, we'll only focus on in this situation when x is a finite set. For example, if x has 5 elements, then you're looking at all the bijections from a 5 element set to itself. Then as you know by now that there are 5 factorial such bijections, because such bijections are permutations only, right? So you'll end up getting 5 factorial many you'll end up getting a group with 5 factorial many elements. Anyway, so let's try to set the stage by setting some of the notations. Yeah, because if you want to write down all the bijections, that's going to be a messy thing, right? So we'll need to add up certain notations that will simplify the the presentation and so on. Okay, so recall that if we have a bijective map f from x to y, okay, in other words, we have a map that is injective and that is surjective too. Okay, so a bijective map f from x to y is a map which is injective and surjective. Okay, and let's introduce this notation, this convention. This is called the array notation. So suppose we have a set x and we denote its elements by x1, x2, x3. Suppose the elements of x can be denoted in this fashion, x1, x2, x3 and so on. Okay, and then we denote the images of these elements under f, where we have a bijection in mind. F is a bijection from x to some set y. We denote the images of these elements under this bijection f by y1, y2, by y1, y2, y3 and so on. By y1, y2, y3 and so on. And now so now just note that what do you need. So we need to just to understand or to indicate this bijective map or to describe, we need to indicate or to mention the images of all the elements of x under this function f. Okay, it doesn't really matter whether f is bijective or not, as long as we have a function f from x to y. Okay, we need to describe the images of all the elements of x under this function f. Okay, then this could be done as follows. So this is something that will be this is the convention that we'll follow. So we'll write the elements of x in the very first row, okay, and then right below x1 and x2 and x3 we will write the images of this function f, okay. For instance, if I mean, just to have an example, suppose we have a function f from 1 to 3 to 1 to 3, okay. We'll have a bijection only because we're going to deal with bijections, so we'll not deal with something which is more general. So suppose f of 1 is equal to 3 and f of 2 is equal to 1 and f of 3 is equal to 2, okay. So yeah, just give me a moment. Or oh yeah, probably this is the classical notation, right, that we used to have in our school days. So yeah, so we have a function which sends f of 1 to 3, which sends 1 to 3, and which sends 2 to 1, and which sends 3 to 2, okay. Yeah, note that a function can also be described in this fashion, but I mean it will just consume too much amount of space, okay. So what we will do is the following. So we will write 1 to 3 in the first row, and right below 1 to 3 we will write their images. Here 1 goes to 3, so we will write 3 below 1. Here 2 goes to 1, so we will write 1 below 2, and here 3 goes to 2, so we will write 2 below 3. So first we write down the elements of the set x, okay, and then below them we write down their respective images, okay. So let's try to have an elementary exercise. Let's try to write down all the bijections f from 1 to 3 to 1 to 3, okay, again following the array notation, not this style, okay. So there are so how many such bijections are there from this set 1 to 3 to itself? There are 3 factorial bijections, that is 6 bijections, okay. And so here are them, I mean here are all these here are all these bijections. So 1 to 3 can go to 1 to 3 respectively, that's fine, okay. And then we can think of something cyclic, for example 1 to 3 could go to 2 3 1, or maybe 3 1 2, okay. And then we can have permutations or bijections which fixes 1, okay, and swaps the remaining, or which fixes 2, swaps the remaining. By swapping the remaining, I mean 2 goes to 3 and 3 goes to 2. You can fix 2 and you can swap the remaining 1 and 3 among each other, that is 1 gets sent to 3 and 3 gets sent to 1, and you can fix 3 and swap 1 and 2, okay. These are all the bijections. I mean, so here we have described all the bijections from 1 to 3 to itself using the array notation, okay. Great. So I mean we'll give a name to such things, and this is customary to call them permutations, and these are precisely the permutations, as you can see. So below 1 to 3 you're organizing 1 to 3 in whichever order that you may have in mind, okay. So this makes sense to call this as permutations, okay. So you start with a set x, then sorry, this has to be x. Yeah, if you start with a set x, then a permutation of this set x is a bijection f from x to a, okay. The group of all permutations, so the group of all permutations of a set x is denoted by perm x, okay. Note that this set of all permutations of a set x, that it does form a group under composition of functions, okay. So you send a pair f comma g to f compose g, okay. So you send a pair f comma g to f compose g. And just to recall this notion of composition, because this is going to be important. So whenever we have two functions psi1 and psi2, psi1 goes from x to y and psi2 goes from y to z, okay. Note that their composition is denoted by psi2 composite psi1, not psi1 composite psi2, okay. So you put the maps in this, I mean in a suitable order, so that the image of psi1 is contained inside the domain of psi2. So the image of psi1 which is contained inside y, and y is the domain of psi2, okay. So please please remember this convention, otherwise things may go wrong, okay. Yeah, so this is the convention that you will follow, okay. So this is a map, so this composition is a map from x to z, and it sends an element x of x to psi2 applied to psi1 of x, okay. Great. And thus if we start with two permutations f and g of x, then f composite g sends an element x to f applied to g of x, okay. And this is an exercise, this is a repetitive exercise that asks to show that the set of permutations of a set x, it forms a group under composition of functions, okay. Great. And now let's go back to our previous example once again, okay, and then see what happens. We try to describe all the compositions or at least a few, okay. We consider this at 1 to 3, then we look at the permutation group perm 1 to 3, which consists of all the 6 elements, and let's try to look at the composition of few elements. So for example, if you take this element and compose it with this one, okay, the second element gets composed with the fourth one, then we end up obtaining this, the very last element. And again if we oops, yeah, I mean, just take few elements and compose them with each other in a suitable fashion, okay, and then one can check that that these equalities hold. Let me explain the first one, okay. There is not much to explain. What I'm trying to highlight is this, just give me a moment, I think it got frozen. Oops. Yeah, it's still in progress. Okay, great. So I'm just trying to explain this. I'm going to explain this equality. So what I'm trying to highlight is that the notion of the composition of functions. Okay. Otherwise, this equality is completely straightforward to show. Completely straightforward to obtain. Anyways, we have got two bijections. Their composition will be a bijection. So how do you do that? So let me try to work it out right in front of you. I already have it written. So to evaluate the composition or to understand the composition of these two bijections or these two permutations, okay, we first write 1 to 3, and then we are supposed to write the images of 1 to 3 right below them under this composite map. So as I have just told you that first we apply psi 1, okay, and then we apply psi 2, okay. So we first apply this map and then we apply psi 2. So if we apply this map to 1, then you know that 1 goes to 1, okay, and now you apply this map to 1, so then it will go to 2. So we have 2 here, and then we take then you take this element 2, and then if you apply this permutation to this integer to this entry to this element 2, we end up obtaining 3. And then this permutation, when this permutation is applied to this element 3, we end up getting what? We end up getting 1. So you should write 1 below it. Okay, so now we are going to apply this permutation to this element 3, and we know that 3 will go to this element 2. And now when we apply this permutation to this element 2, we know that 2 goes to 3, okay. So you obtain 3 here, okay. This is the way you can you can express composition of two, composition of two permutations in the array notations, okay, easily. And what you see from equation 5th and 7th, the first one and the third one, is that this is a non-abelian group, okay. So here you had these two permutations, and here we have just swapped the order, and you see that the elements that you have obtained, they are different, okay. And yeah, okay. So here this exercise was in this exercise it was asked to show that the set of all permutations of a set X forms a group under composition of functions, and this group has a specific name. This is called the permutation group, okay, of the set X. And when we have this set 1 up to n in mind, then the permutation group of this set 1 up to n, that is the group perm 1 up to n. So this gets a specific name. This is called the symmetric group of order n, and it is customary to denote it by Sn, okay. This is a symmetric group of order n, and this is denoted by Sn. Great. And we have already described S3, okay. That is a set of all, that is a group, that is a permutation group consisting of all the bijections from 1 up to 3 to 1 up to 3. That is 1 to 3 to 1 to 3, okay. And we have already observed that S3 is non-abelian, okay. If you work on S2, that is if you are interested in understanding the bijections from the set 1 to itself, then there are two such bijections only. One is the quote-unquote the identity one, which sends 1 to 1 and 2 to 2, and the other one is the one which swaps 1 and 2, that is it sends 1 to 2 and it sends 2 to 1, okay. And this is straightforward to see that this is an abelian group, okay. You also know that any group of order P has to be abelian, right? Okay, great. So now maybe we can move on to some bigger SNs. That is, we can move to some SN where n is a bit large. Okay, maybe we can look at S7. So this exercise says that to us to show that S7 is a non-abelian group. Okay. Yeah. So as you see that I have a huge. I have got two huge permutations. Okay, and I compose them in two different orders. Compose them in this order first, and then I change the order. What I end up obtaining, these two are two distinct elements. Okay. Yeah. So at this stage, you might wonder from where did I get all this motivation to consider all this. You first note that I haven't changed 4, 5, 6, 7. Okay. In fact, the permutations that I have considered here, note that it sends 1, 2, 3 to 2, 3, 1. 4, 5, 6, 7 there they go to themselves. Okay, so here 1, 2, 3 goes to 2, 3, 1 and respectively, and the second permutation that we have that fixes 4, 5, 6, 7 and sends 1, 2, 3 to 1, 3, 2. Okay, and note that this is precisely that we had in the context of S3 in equation 5. Okay, so the idea of establishing that S7 is a non-abelian group has been borrowed from what we have already seen or done in the context of the group S3. Okay, and you'll get to see more instances of this kind of this kind of situations where to solve a problem for Sn for some large value of n, or maybe for general n, we first work out some we first work out certain smaller instances or some elementary instances. That is, we work on Sn for some small values of n. Again, that is going to be difficult because S3 has got 6 elements, and then inside S4 we have got 24 elements. Probably that is still manageable, but whenever you move to S5, there's got 120 elements. So it becomes practically impossible to manage by hand, or practically manage all the elements by hand. But again, we try to draw some motivation or some hint by first working on this essence for some small value of n. Anyway, so as you see after that the composition of these two has to be equal to the function that will send 1, 2, 3 to 2, 1, 3. Okay, and will fix 4, 5, 6, 7. The point is that if we apply this composite map to the integer 4, then this first permutation will send 4 to 4, and the second one will also send 4 to 4. Okay, so if you have two bijections, okay, and if you are, for example, if you have just two functions that sends 4 to 4, suppose both of them sends 4 to 4, so when we apply their composition to the element 4, the image will be 4. Okay, and for the same reason, for the elements 5, 6, 7 also go to themselves under the composition of these two. Okay, and for 1, 2, 3, okay, you just you can show that this is indeed equal to whatever we have on the right hand side. Okay, so try to establish, okay, on your own. You will see that you'll obtain some better understanding of this array notation. Okay, this is so straightforward that there is nothing to explain. It is better, it is much better, and it is effective. It is effective if you verify this equality on our own. Okay, so let me not describe this. Okay, yeah, in fact we can extend this argument further to show that Sn is non-abelian for any n greater or equal to 3. Okay, so we'll do the same thing. We'll have two permutations sigma and tau, which will send 1 and 2 and 3 to 2, 3, 1 respectively, what you have done just before, and it will fix the remaining elements. Okay, so it will send I to I for other values of I, that is for I greater or equal to 4, and the permutation tau that we will consider, it will send 1, 2, 3 to 1, 3, 2. Okay, it sends 1, 2, 3 to 1, 3, 2 respectively, and then we will see that sigma composite tau is not same as tau composite sigma. Okay, so this is something that we have already observed in the situation in the context of the group S7. Okay, by reviewing the proof at least once or twice, we'll immediately see that these two compositions are not identity. Okay, and that will establish that Sn is non-abelian because we have come up with two elements sigma and tau such that they do not commute, or their composition when depend on the order in which we take them. Okay, yeah. Now that we have learned certain uh, uh, now that we have seen these permutation groups or the symmetric groups, it will be good to have certain interesting exercises in the setup of what we have learned a couple of lectures back. So let's try to describe Hom S2 comma Z mod 2Z. Okay, so that's your first exercise, and then you can try to count how many elements of this Hom set they are isomorphisms. Okay, and then you can try to show that S2 is isomorphic to Z mod 2Z. Okay. Okay, sorry, great. So let's conclude this discussion here, this lecture here.